All right, example 5, instantaneous velocity at any point. The distance a bumblebee flies along a path is given by this function p, where t is given in seconds and the distance of the bumblebee from a starting point is given in inches. That means p is calculated in terms of inches, p of t. Find the equations for the instantaneous velocity of the bumblebee at any point in time. So to do this, what we would say is that we know that the limit, so let me back up here, the velocity will be equal to the limit as h approaches 0 of this function. So I'll say p of t plus h minus p of t all divided by h. That's the formula we're going to use here. So plugging in my values here to solve for this limit, it seems as we're going to plug in t plus h in here. And so we'll have 12 times t plus h minus 6 times t plus h cubed, quantity cubed. That'll be fun here in a moment, plus 1. And then we will have minus, and I'm going to throw in here a different color. Now we just have this equation p of t itself, minus 12t minus 6t cubed plus 1. And all this will be divided by h. Now, before I go too far in trying to simplify or trying to FOIL this out, I can state confidently that this plus 1 and this, when I distribute here, we're going to distribute all the way through here. This will become a minus 1. The plus 1, the minus 1 will cancel one another out. And so we'll see what happens to the rest of the equation as we go. I can see that I'll have a 12t here, and I minus a 12t there. So I'll go ahead and remove that. And we will have to, I would call it a FOIL, but it'll be more than a FOIL on this portion. So now let me rewrite what we have here. We have limit as h approaches 0. Here I will have 12h. The 12t minus 12t are already canceled out. So I have the 12h minus, okay, and now we need to do what I would call a FOIL, but it's not truthfully even a FOIL, it'll be more than that. I'm gonna write it over here, t plus h times t plus h times t plus h. And it gets multiplied by -6. That's what cube looks like. It happens 3 times. So we could multiply here the first time through. The -6 will just distribute to this first parenthesis. So I'd have -6t minus 6h. And then this would multiply. If I wanted to FOIL out this end, I would have t squared plus an ht plus another ht is going to be 2 ht's if you've seen me FOIL a few times, plus h times h, which is an h squared. So now I'll multiply these two groupings. I will have here a -6t cubed minus 12ht squared and a minus 6h squared t. Here we have minus 6h squared. No. That's off, sorry. T squared minus 6ht squared. Here I have, this will be a minus 12h squared t. And then finally, right there, minus 6h cubed. When I combine my like terms, this is going to be -6t cubed minus 18ht squared minus 18h squared t minus 6h cubed. Okay, so that's what's coming next in this middle portion right here. So we have a minus 6t cubed minus 18h squared t minus 18ht squared minus 6h cubed. Finally, when I distribute this portion over here, we would have minus a negative 6t cubed, which is a positive 6t cubed, and all this divided by h. All right, so let's see if we can cancel anything now. When I look at this listing in here, I see I have a minus 6t cubed and a positive 6t cubed. And then I also share an h all the way across. I could divide out a 6. I'll just put that in the front of the limit right here. So 6 times limit h approaching 0. I'm dividing everything by 6. And I will GCF this h out. So I've already taken out a factor of 6. So this will be left over 2 here. Minus 3. One of those powers of h is gone. ht. Minus another 3. This h is gone, so it's just t squared. Minus 6h squared. All of this divided by h. I can see that my h's get simplified, which means this is going to be equal to 6 times the limit. And now that that is a, I actually don't need to write the limit again. Now that this is polynomial, I can just do a direct substitution. 6 times the value of 2 minus 3, 0 times t, because h is approaching 0, so I'm substituting in 0 there, minus 3t squared minus 6 times 0 squared. So multiplying by 0, those values will simplify out of there. Let's see what we come up with. We'll have 6 times 2, which is 12. 6 times 2 is 12. And then here, minus 18t squared. That right there appears to be my velocity equation. So that would be v of t. V of t would equal 12 minus 18t squared. That's my velocity function at any point in time. And that's what we were supposed to find it for any point in time. And so again, if you wanted to relate this to the graph, like what does that do for me? Let me graph the first function here, p of t equals 12t minus 6t cubed plus 1. And we're saying the velocity vector, or the velocity function, I'm sorry, velocity function is 12 minus 18t squared. Okay, so when you look at them, they don't look alike at all, but given a certain point in time, if we have any certain value, I don't know if this will allow me to do a certain t, if that's going to throw off this problem. Yeah, it will. But what would happen is if we were looking at this, and you want to know the velocity or at any point in time, let me just say like p of 3 here. Rather than do it that way, let me show you a table. Okay, so here's the values. So for any one of these points in time, if you want to know what's the velocity here at time 0, what's the velocity, what will happen is this graph at time 0 will show you what the instantaneous velocity is, or what the slope of that line is. So at time 0, it's 12. That means the line going through this point right there is 12. And if you're like, can you prove that to me? Yes, I can. Let me take that off for a second, velocity. And if I did y equals 12x, that's that slope. But to make it go through this point of 0, 1, I'll use point slope. So minus 1. And this minus 0. I know you don't have to have the minus 0. You can see that that is a tangent line going through that point at 0, 1. That is the slope of that line going through. It just touches it one time, it goes perfectly through it. Just the same, if let's say we wanted to find the tangent line or the slope here at 1, 7, what I would do is I would come over here and say, all right, at 1, 7, it looks like the slope would be negative 6. So if I did negative 6 at the point the x was 1, the y was 7, you can see that I have a tangent line coming through right here. I'm using the value at 1. Here, there's 1, 7. That's the position. This function here is the position function. This one right here, it's what you'll learn is called a derivative. It's telling you the slope or the instantaneous velocity. Its velocity at 1 time of 1 second is -6. So when I plug that in, using this as the position and -6 is the slope, you see that the value works out perfectly for a tangent line. So with all that, that's kind of the extra. That's how the graph looks. Let you try this problem here. Stop the video if you need more time.